Hello everyone. So in this video, we will be doing our Jupyter notebook testing, and it is a very important video. Okay. So first of all, uh, okay. So let's create one notebook directory. So let's create one notebook directory. Inside notebook directory, let's create one ipynb file. So let's write notebook.ipynb. So this ipynb is the extension for your Jupyter notebook files, right? First of all, go to your extensions, VS Code extension. Make sure your Jupyter is installed. Okay, search for Jupyter and just install this. Okay, okay. So basically, it gives you Jupyter Notebook support, right? Now, just open a code cell and press Shift and Enter. Okay, so it will ask you to select a kernel source. So go with the Python environment, go with the recommended one. So it is your current virtual environment. So select it. Okay, so you can see now here it is venv Python 3.1.2 something. Okay, just go again, go to any code cell, press again Shift and Enter like this. So it will ask you to install the IPY kernel package. Just install it. Okay, so you can see it has started installing your IPY kernel. Without IPY kernel, you can't write any code of Jupyter Notebook. Okay, so we have to install this IPY kernel. Okay, so let's give it time so that it can install IPY kernel successfully. After it has been successfully installed, we will start writing our Jupyter Notebook testing codes. Okay. Okay, so now you can see your Jupyter Notebook kernel, IPY kernel is successfully installed. Now let's start writing our code. First of all, let's see where our data is. Our data is in artifacts raw data.csv. Okay, remember this part. Let's go with imports. First of all, we need some imports. Okay. Uh, First of all, our basic imports. Import pandas as pd. Okay. Then import numpy as np, then import matplotlib dot pyplot as plt, then import cborn as sns. Okay, and one more thing we can do, just write percentage matplotlib in line. Okay, so that your all the graphs are we can say in a good manner. Okay, so that they can be how I say that, basically your graphs will not spread out too much. Okay, they will be in a fixed shape. Okay, they will not leave the Jupyter kernel size. Okay, I hope you are understanding. Now we will import one more things, import warnings. Okay, and I will write warnings dot filter warnings, and I will write ignore. Okay, now what is this doing? This is a by default module in Python, and why we are writing warnings dot filter warnings ignore. You generally get some warning messages when you are working with Jupyter Notebook testing. Okay, so it will ignore those messages so that your kernel will look clean. Okay, that's the only use of this. It's optional. You can write or you can not write. It will have no effect on your code. Okay, let's run it. So it is importing all the things. Okay. Hmm. Okay, so you can see there is a tick here. Okay, you can see there is a success message. So you can move forward. Now we have to read our data. So we will read data using df equal to pd dot read csv. Our data is in artifacts raw. Okay, but currently we are in notebook directory. So we have to go outside this notebook directory. So you will write dot dot slash. Okay, now go inside artifacts. Now go inside raw. Now go to your data.csv. Okay, like this. Now you can check your data, df.head. Okay, so it is your data. This data I have already told, it is related to your smart industrial machines. Okay, these machines generally uses AI and something. Okay, and this is data is from your sensors. These machines have sensors. Okay, so this is your machine ID, operation mode, temperature, vibration, power consumption. Okay, like this. So first of all, let's check the shape, df.shape. So you have around it's 1 lakh, right? So you have around 1 lakh rows and 13 columns. Okay, so you can see your columns here. Okay, now let's understand these columns one by one. Okay, because if you don't understand your data, you will not be able to make uh, any predictions on that type of data. You have to understand your problem before going through the solution of that problem, right? So first of all, first column is timestamp. Now what this timestamp is telling us, it is telling you the date. Okay, this is the date and this is the time. Okay, when that particular data was recorded. Okay, okay, whenever that every data was recorded, this is the date and time for that. Okay, then you have machine ID. Every machine is given a separate ID. Okay, just like you get separate roll numbers in your colleges or schools, same machines also get uh, unique IDs to distinguish between them. So this is a machine ID. So this machine has 39 ID, it has 43, it has 8, 29, like this. Then we have operation mode. Now let's check the operation mode. Let me copy this. Let's write df operation mode dot value counts. Wow. Copy, cut this, dot value counts, like this. So basically there are three operation mode: active, idle, maintenance. Now what are these three operation mode? Whether the certain machine is in active mode, it means it is running. Okay, when this data was recorded, that machine was running. Idle means this machine is not running, it is in idle state. It is in a working condition, but it is not running. Okay, it is working but not running. Now we have maintenance. Maintenance means this machine is this machine can't be used. Okay, it is not in a working state. Okay, it is under maintenance. You can see 70,000 around machines are active. They are currently running. 20,000 were in idle state and around 10,000 machines were in maintenance condition. Okay, then we have temperature C. C means Celsius. Okay, so uh, it was temperature C determines your machine's operating temperature. Okay, when this data was recorded, what was the machine temperature? Okay, so it was around 74 degrees Celsius. Okay, machine was in idle state, and you can also distinguish uh, idle machines have a lower temperature because they are not working. If a machine is active, generally it will be producing more heat. Okay, if a machine is active, so it will be producing more heat, and hence the temperature will rise. So you can see it has idle machine has 74, while active machine has 84. Okay, now you will be seeing you will be saying this machine is also active, but it only has a temperature of 44. But that also depend on the machine size, right? If a machine is small, obviously its heating properties will be far less as compared to the big machines. Okay, so that depend on the machine size also. Then we have another column, vibration hertz. Okay, uh, this column determines the frequency of your machine vibration. Okay, basically this parameter is used to determine whether your machine is wear and tear. Okay, it helps you determine your machine wear and tear. If a frequency of a machine is too high, so it will go through wear and tear more fastly. Okay, then we have power consumption in kilowatts. KW means kilowatts. So it's basic column. Basically, it will be the power consumed by that certain machine. Okay, So it is around 8 kilowatts. Maybe it's a big machine, and it is a 2 kilowatt. So maybe it's a small machine, or maybe it was run for longer time. It was run for a smaller period of time, like that. Then we have network latency. MS means millisecond. Okay. So network latency means, suppose this sensor recorded our data. Okay, that particular sensor on the machine recorded the data that you are seeing here, and it has to send that data from here to your server where this data was stored. So what was the network lag between sending that data? So that is your network latency. Okay. Uh, then here it's your packet loss percentage. It is in percentage. Okay, 0.20 percentage. It means 20%. Right? It is 20%, right? Okay, 0.20% only. Okay, okay, okay. I thought it is in decimals. Okay, 0.20%. It is also telling when that data was sent from sensor to your server, what was the packet loss, okay, during the transmission. Basically, this feature will affect your real-time monitoring. If a packet loss is too high, okay, so data from sensor will reach the server in a very large time. Okay, so it can cause hindrance to our real-time monitoring. Then you have quality control defect rate percentage. It is also in percentage: 7%, 4%, 0.45%. Okay, uh, so it is the percentage of defective products. Okay, it is a percentage of defective product. Then you have production speeds unit per hour. Production speed unit per hour. So basically, these all machines are your manufacturing machines. Okay, these are your smart manufacturing industrial machines. Okay, that's why we are seeing the term production speed, because manufacturing means to produce something. Okay, so this production speeds unit per hour. How many units a particular machine is making in an hour? So it is making 477 units. It is making 398 units of products, whatever the product it is making. Then predictive maintenance score. It is a score. Uh, Basically, it is indicating a likelihood of a machine failure. Okay. Basically, it is telling you, mm, the higher the maintenance score, okay, higher the chances of that machine failure. Okay. If a machine is requiring too much maintenance, okay, there are chances it can cause failures. Okay. So machines should be of less maintenance so that it will also do your cost cutting also. Then error rate. Okay, what is this error rate? Basically, it is the percentage of operational errors or failures that was detected by the sensors or machines. Okay, and at last, this is our output column. Okay, whether the machine is of low efficiency. Low efficiency means uh, it is taking more power, it is consuming your more money. Okay, in maintenance and everything, but it is not giving the desired output that you want. Okay, suppose it is taking too much electricity. Okay, it is producing average number of products. Okay, it is requiring high maintenance, so its efficiency is low because you have to invest more and you are getting profit less. Okay, then there is medium, then there are high. High means, uh, let's check this efficiency status. We don't have any fourth option, right? Should be three only. Let's check. Okay, low, medium, high. So most of the machines are of low efficiency status, and some are of medium, and very less are of high. High means these machines require less electricity, less maintenance, but still giving us better results. Okay, although these machines will be costly, of course. Okay, you can also, I can also give you an example for this. Suppose let's take a refrigerator, or let's take a AC. Let's take one AC with 1 star rating. Okay, you get a 5 star. Uh, we can, that is, I think, efficiency rating only, right? 5 star AC, 3 star AC, 1 star AC, 2 star AC, like that. Okay, let's take one star AC, another 3 star AC, and last one a 5 star AC. So which will be the most efficient? Of course, 5-star AC, because it consumes less electricity and give you the same amount of coolness, right? 3-star AC, it consumes average amount of electricity and gives you good coolness. Then 1-star AC, it consumes high amount of electricity and give the same coolness as a 5-star and 3-star only. Okay. Although the low efficiency machines are lower in cost, okay, as compared to the machines with higher efficiency. You can also see a 1-star AC cost too much less as compared to your 5-star AC, like that. Okay, so now you have understood, I think, all the columns of your data. Now let's proceed. First of all, let's check over all the columns. Okay, df.columns. Okay, now I have to show you one more thing, df.info. Okay. Okay, info should have a bracket like this, and you can see here this timestamp is treated as an object. Okay, but it should not be treated as an object. It should be treated as a date time, because you have a data type, date time also, right? So let's make our timestamp as date time instead of a object. Okay, so from here our basically data processing is starting. So let's name it data processing, like this. Okay, so what you will do basically, you will write df and just write timestamp, okay, equal to pd dot to date time. So it will convert this column to date time. Okay, in date time you will pass df timestamp. Okay, uh, and you can just write errors equal to codes. Okay, so if any errors are there, it will handle them during the conversion. Okay, now let's run it. Now let's check our df.info, and now you can see it is now in date time instead of object. Okay, so good for you. Okay, now it's done. Now let's move forward. Let's check for missing values first. Okay, df dot is null dot sum. Okay, it should be dot, like this. So you can see there is no null values here. Good for you. Df dot duplicated dot sum. There is no duplicate values also. Good for us. Okay. Uh, we don't have any null values and duplicate values, so we don't have to drop them. Okay. So now let's convert the columns. Okay. Now let's convert the columns. Basically categorical columns. You can see we have converted timestamp, right? But some of them are remaining, like your operation mode and your efficiency status. Okay, so let's name them uh, categorical categorical columns equal to, let's take them from here only. Okay, so one is your operation mode, let's paste it here. Another one is your, what is another one, efficiency status. These are your categorical, sorry, object data types, so we have to convert them. Okay, like this. So these are your categorical columns. Now we will be converting them into category. Instead of object, they should be a category. Okay, because category is understood by machine learning. So what we will do, you will loop into these two columns for column in categorical columns. Basically, now you are changing the data types only. First of all, you change timestamp from object to data time format. Now you are changing these categorical columns from object to categorical category format. Okay. You will see df call equal to df call dot as type, and inside as type you will write category. Run it, and if I run my df.info now, you will see it is in date time now. Your operation mode is now in category instead of object, and your efficiency status is also in category instead of object now. So that's good. Okay, so I think you have got the gist what we have done. First of all, we converted timestamp from object to datetime. Then we converted these categorical columns from object to category. Okay, so this was all your data type changing. Okay, let's do our EDA also. Should we do EDA here only? Let's do here only. Okay, let me create one markdown. Let me create one. Sorry, EDA. Let's type EDA. Okay, let's do some visualization and all. So first of all, we will plot histograms for all the numeric features, because you can see most of them are numeric features. Okay, float, 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 float. Okay, and one integer also. So let's plot histograms for all the numerical features, and column plot for efficiency status and all. Okay, now let's check. First of all, let's check all the numerical columns. So I will write numeric calls. Okay, so I will write df dot select data types. Select data types include np dot number, like this, dot columns dot to list, like this. Okay, now you can see your numeric columns are what? Just copy it, paste it. Inside this numeric columns, all the numerical columns are stored. All the numerical columns are stored. Okay, you can see there is no efficiency status, there is no operation mode. Rest all of them are there. Okay, you can also check. I think length will be 11. Overall, there are 13 columns, right? But it should be 10. Okay, okay. I think we removed something. Okay, one is timestamp also. Timestamp is a date time format. Okay, so it will not be integer. So we have excluded timestamp and operation mode and efficiency status. So overall 13, but these three are excluded. So we have 10 numerical columns. Okay. Now let's plot histograms for all these numerical columns. So I will write for, I will loop into each of the numeric columns for column in numeric columns, like this, and I will write plt dot figure. Let's pass the fixed size equal to, let's give it 5 comma 5 only. Okay, and let's plot it using hist plot, SNS, using cbond hist plot. Okay, in hist plot you will pass your whatever the numerical column is, df call, and let's set kd also equal to true, so that we can get our kernel density estimation also. And let's set the bins to 30. Okay, now let's give title plt dot title, and we will write title as f string histogram. It's histogram, not histogram. Histogram for df column, like this. Now let's show them plt dot show. Okay, let's press enter. Okay, so we are getting histogram for 0. What is this? Why we are getting this much? Let's fix these using x label and y label also. It's not good in looking. So I will write plt dot x label. I will write here column, whatever the column name is there. Make sure the column name is there. Okay, on the x label. And plt dot y label should be your frequency, like this. And I think we should not name it df column, it should be only column. That's why we are getting this much. Okay, it should be column, histogram for the columns. I think now it should be good. Check. You can see now. Okay, histogram for machine ID, not necessary. Machine ID is a unique identifier, so we will remove machine ID later. Okay, so we don't need machine ID. Yeah, you can see for temperature. Okay, so you can see the most of the machines have temperature. There is a uniform distribution for temperature. Okay, there is not much skewness in the data, so it's good. For vibration also, there is a very uniform distribution. Power consumption also uniform distribution. Network latency also uniform distribution. Packet loss also uniform distribution. Okay, quality control defect rate also uniform. It's too much uniform. Okay, error rate also uniform. Everything is uniform data distribution. Good for us, but I think this is a synthetic data. There is not this much uniform. This is too much uniform. Every column is uniform. Okay. Okay. Now, let's make a pair plot. So I will write SNS dot pair plot, and I will write df numeric columns like this, and I will pass plt dot subtitle. Okay, subtitle. Let's write it as pair plot for numeric features like this, and after that I will write y equal to 1.02 like this, and I will show it plt dot show. Let's press enter. It will take some time to generate a pair plot for all the numerical columns. So basically it will show you the relationship between each numerical columns. That's it. Taking too much time, I think. Okay, so it has generated. Okay, so as you can see, all of them are uniform. Okay, all of them are equally spreaded. So most of them are uniform only. So I think it is a synthetic data. Okay, because there is too much uniformity. Okay, but no worries. We will deal with the data like this only. Suppose we get a real data also, so you can do the same processes. No worries. Okay, but there you will get a more better insights. Okay, because temperature, because you see, temperature and your this error rate, they have a uniform distribution with each other. Okay, so this may be a synthetic data, maybe not. It should be a synthetic data. It must be a synthetic data. Only, only then I think it will make sense, right? Now, let's make some other graphs also for our categorical columns. Then we will proceed with our feature engineering. Okay, that is a part of data processing only. Okay. Now let's make a count plot for our basically efficiency status. Let's make it. I will write plt dot figure like this. Let's set the fix size equal to 5,5. Okay, it's a decent size for Jupyter notebooks. I will write SNS dot count plot like this. On the x-axis, I will pass my uh, efficiency status column like this. On the data, I will pass my df, and on the palette, I will pass, you can pass schoolworm if you want. I will pass this time viridis like this, and I will write plt dot title. Okay, and you can give it any title. So I will write just efficiency status count plot like this. Okay, and x label, y label you can give. I am just showing you the graph plt dot show. Okay, so you can see most of the machines are of low status, sorry, low efficiency. Then around 25% of them are around medium, and very less, around 2000 3000 are of high efficiency status. Okay, so we have already discussed that in during the our features introductions also. So I think there's not much EDA you can do, because this is a, I think, synthetic data. So there is not much EDA you can do, although it's a unique data. Okay, sensor data are very unique. Okay, so if you ever get a chance, work with sensor data, because those are real world data. Okay, generally machine learning engineers have to deal with sensors data only, right, to make their predictions. Now let's start with our data processing only, but it is our feature engineering now. Let's write fe, and let's do our feature engineering. First of all, what you will be doing from the timestamp, let me show your data. Tf.head, okay, it is in markdown. Let me give a code cell. Okay, tf.head, here's your timestamp column. Okay, so what we will be doing, uh, we will be extracting this year separately, this month separately, this day separately, and this hour separately. Okay, so for this, what you will be doing, I will write df year. I will be forming a new column inside my data frame, and I will be extracting df timestamp dot dt dot r. Okay, like this. And let's do the same for month and date also, day also. Month equal to df timestamp dot dt dot month, because you can't work with the timestamp data directly. Okay, so you have to extract those features separately. You have, I think you have learned this during your feature engineering sessions, from wherever you have learned. Okay, then we have our day, and we have df, then we have timestamp, then dot dt dot day. Okay, it will extract our day. Let's do the same for hour also. So let's, you can do the same for minutes and seconds also, but we are not going that much deep. Okay, hour is fine. Okay, timestamp dot dt dot r like this. Let's run it. Now let's check our df.head. Let me run this cell again, and let's go at the last. You can see year 0, uh, month 1, day 1, hour 0. Why it's year 0? It should be 2024, right? Okay, I think there is a issue. Why it's taking year as 0? Okay, I have taken dt.r here in place of year. Okay. Now we have to run the cells again. Let's go to the top. Let's run these cells again. Let me read the data again. Okay. Uh, let me do the data processing again. Okay. I'm not doing the EDA. Okay. Now let's come to our, just go below. Now let's run it again. Okay, now you will see df.head, and if you will see, now you are getting year 2024, month 1, day 1, hour 0. Okay, so now it is good. Okay, that time I placed hour here instead of year, that's why we were getting error. Okay, now you can drop this timestamp column if you want. Okay, you can just remove this if you want. Let's remove these. Let's remove df dot drop, okay, columns equal to, let's remove certain columns that we don't want. First of all, it will be timestamp because we have extracted the data that we need. Okay, so it will be our timestamp. Then it will be uh, machine id. We don't need this machine id. Let's copy it and paste it here. Okay, and rest we need. Okay, because machine id is a unique identifier. So let's remove them and let's set here in place equal to true, so that it will make permanent changes. Let's run it. Now let's check the shape. It is 15. Okay, if you want to check, let's check tf.head. Okay, now there is operation mode only. Your timestamp and machine id have been removed successfully. Okay, so let's remove this. Okay, now what you will be doing basically, uh, let's go with, I think this much feature engineering is only required. Yeah, that's good, I think. Okay, so now let's start with our first of all label encoding. Okay, we will label encode our efficiency status also. Okay, so I will write label encoder equal to, initialize the label encoding. Okay, we have to import it first of all. So I will write from sklearn dot, it is in pre-processing, right? Import label encoder, label encoder, like this. Now I will label encoder. Okay, I will write df efficiency status, or I can make a new column. Let's make a new column, efficiency target equal to uh, label encoder dot fit transform. I will apply this fit transform on df efficiency status, and we will get a new column, efficiency target. Let's apply it, and you can see I will write df dot head. Let's give only two columns. You can see at the end, efficiency status low, it means it is 1. So it has encoded low as 1. Okay, same, it has encoded high as 0 or medium as, like this. Okay, you can check using this also, df efficiency status dot value counts. Okay, same way, df efficiency target dot value counts, like this. So you can see low is encoded as 1, medium is encoded as 2, and high is encoded as 0. Okay, got it. Now let's define our input variables and output variables. Okay, so what you will do, let's define our x equal to df Let's define our input columns here first of all. I will write here features equal to like this. Okay, and I will write here df dot columns after this df dot columns. Okay, so these are our current columns. This efficiency target will be our output column, right? And these are all our input columns, not this efficiency status. Okay, this is the just the replica of your efficiency target only. So I want operation mode, temperature Celsius, vibration hertz, power consumption, packet loss, quality control defect, production, maintenance score, error rate also. Okay, so these I want. Just I will copy here. Okay, after that I don't want this efficiency status. I want this year, month, day, and hour. So just copy them and paste them here. So these are your all the features. So I will pass X means your input features. So in input features, all of your these features will be there. Okay, so you can check your X dot columns. Okay, so the above features are there. Okay, which you defined in the features. Only those features are in the input feature. Okay, in the same way, let's define our Y. Y will be our TF efficiency target. Okay, so you have your input columns now and output columns now. Let's scale them. Let's scale them. I will import from sklearn dot preprocessing import standard scalar. Okay, let me initialize my scalar equal to standard scalar, and I will write x scaled. I am performing scaling on this x. Okay, I am writing scalar dot fit transform like this. Fit transform x. Okay, so it has done. Could not convert string to float. Okay, so I think it is related to your operation mode, right? Okay, so we have to encode our operation mode also, I think. So let's encode our operation mode also. Just copy it, paste it, and I will write here operation mode this, and I will write operation mode. Let's run it. Now our operation mode is also encoded. Now it should work. Okay. Mm, I don't know why it's not working. Let me check my df.head. Okay, operation mode is there, everything is there. What it's showing basically. Okay, could not convert string to float. Could not convert string to float. Okay, let me fix this issue. Okay, so we were getting this error. Let's remove this standard scalar for now. Okay, let's remove this. Okay, and if I check my x dot columns, sorry, x dot head like this. Okay, so it was causing issue because we have changed it in, we have label encoded this df, but we have not encoded it in x, right? So I have to encode it again. Just run your features again. Okay, x features again, y again, now scalar, and now you will see it has been encoded. Okay, the problem was that I have encoded them in df, but they were not encoded in x, and scalar was working on this. operation is on X. Okay, so now let's do the same scalar, standard scalar. Now if you will write X scaled equal to scalar dot fit transform and just apply on X. Okay, run it. Now you can see it has successfully run. So for now, input columns are in X scaled, output is in Y. Okay, so you have done the scaling now. Okay, so now let's split our data into train test split. So I will write from sklearn dot model selection import train test split. Okay, so I'm writing X train, then I want X test, Y train, comma Y test, like this. I'm doing train test split. I will be splitting my X scaled. Okay, I will be splitting my X scaled. That is your input data. Output data is in Y. Okay, test size, let's take it 0.2. Okay, and let's give a random state of 42, like this. Okay, and give a stratify equal to Y. Let's run it. Okay, so now your data have been splitted successfully into extreme, X-test, Y-train, Y-test, of which X-train and Y-train will be used for your training, your model. X-test will be used for making the prediction from the model, and then we will compare that prediction with our Y-test, that is the actual values. Okay. Okay, so which machine learning model should we take? You can do your model selection, train each model which we have done in project 1, project 2, like that. But I will be taking very simple model, that is our logistic regression, because first of all it is a very synthetic data. Okay, all our data is very uniform. Okay, so for the uniform data, logistic regression works pretty good. Okay, and since we will be deploying this in our VM instances later, okay, that is the most important part of this project. Okay, so I think we should take a project that has a smaller model, faster model, so that we can work easily, because GCP provides you only a limited amount of storage and processing power. So let's go with the logistic regression only. So I will write from sklearn dot linear model import logistic regression. Okay, let's initialize our logistic regression. CLF equal to logistic regression, and let's give it a random state of 42 only. Okay, max iteration, let's give it by default value, that is 1000. Okay, and let's CLF dot fit, let's train our model on X train and Y train. Okay, so our model is trained because it is fast. Okay, now let's make our predictions. Y predict equal to model, sorry, model is CLF dot predict on X test. We are making prediction on X test and storing those prediction in YPred. Okay, so we YPred have our prediction now. Okay, let's calculate the accuracy from sklearn dot metrics import accuracy score. During our model training phase and model evaluation phase, I will import more metrics like your recall, precision, F1. But for now, let's go with accuracy score since it is our Jupyter notebook testing. Okay, so I will write accuracy score. You will pass your Y test, that is your actual value, and now your Y pred, that are your predicted value. So it will compare them. Okay, so it is giving us 0.91. It means 91% accuracy. That is a very good accuracy. Since we are using logistic regression, suppose if you have used a higher model like XGBoost, Gradient Boost, Random Forest, so you have easily got around 98, 97 easily. Okay, and suppose if you have hyper tuned the logistic regression also, you will get around 93, 94 easily. Okay, and you can do one more thing. Let's in the metrics only, let me import a classification report. Okay, let's print a classification report also. Same, pass your y test and your y pred. Okay. Okay, it should be in print classification report. Okay, so your precision is around 0.85 for your 0th class. Okay, so 0th I think is denoted by high. Okay, high efficiency machines. Okay, so f1 around 0.849578. You can see all these. Okay, so pretty much good. Precision, recall, f1 score, accuracy, everything is pretty much good. Okay, and we can't make ROC AUC score. Okay, because this is not a binary classification. We have 3 classes. Okay, so you can't do ROC AUC here, right? Okay, what you can do basically, we can do one more thing that is called permutation importance. Permutation importance. Okay, I will tell you what is this. Basically, it will tell you the importance of the features. Okay, like just you get in random forest inbuilt feature importance, XGBoost inbuilt feature importance. Same here also, but you have to import something. First of all, you have to import this permutation importance. So from it is in from sklearn dot inspection. Okay, import permutation importance. So you have to import it. Okay, let's run it. Now you are ready to go with your permutation importance. Okay, so for this you will write the code. You will write result equal to uh, permutation importance. Okay, you will use your permutation importance. First of all, you will pass your model here. Model is your CLF, then your X test and Y test. So it is your X test and your Y test. Okay, then number of repeats you have to pass. Number of repeats, let's set it 10. Let's give it a random state of 42 only. Okay, and number of job you can set it -1 and jobs equal to -1. Okay, like this it is your result. Okay, so it will basically calculate your result. Let's check what is this inside this result. Okay, so these all things are inside the results. Importance, mean, importance, standard deviation, importance is arrays, like this. Okay, now you will see how we will make it in a graphical way, or we can in a pandas data frame way. Okay, for this you will write, let's make a importance df equal to, I will create one pandas data frame. Pandas data frame. Okay, inside pandas data frame I will create one column feature. Okay, feature will be my features only. Okay, which we have defined above. Okay, all the features that we are taking, these features. Okay, I have defined them above only. And my importances will be, importances will be, you will write result dot importances, importances mean. Okay, so mean you will be accessing this. Okay, importance, I think I have written the wrong spelling. Let me copy from here and paste it here. Okay, like this. Okay, so now you have importances df. Let's check this importances df. Okay, so this is your operation mode, these are your these, this is your this. So what you can do, you can just sort the values. Okay, what you can do, importances df dot sort value, so that you can get the top value above. Sort values by import. Okay, you have to pass this column name. Copy it and paste it here, and we will set ascending equal to false. Okay. Okay, so you can see this error rate percentage is the most important feature. Okay, it has a 0.23 contribution. Then you have production speed 0.117, then network latency, and the least important is month. Okay, and these are very least important. You can remove these if you want. It will not remove. Okay, if you want, you can just go with these top 5 also. Okay, then also you will get the 91% accuracy only, right? Okay. Okay, so with this, your Jupyter Notebook testing is done. Now you can, what changes you can make? You can use more advanced models. Okay, you can use other data sensors. Okay, you can use other sensor data. Okay, Kaggle have a very wide variety. Okay, you can just go with any sensor data and just implement your own logics and all. Okay, you know machine learning, basic machine learning, and MLOps. I am teaching you. Basically, I am teaching you technologies of MLOps that are used in production. Okay, right? So you can do one more thing. You can do hyperparameter tuning here in the dataset to increase your model accuracy, right? Okay. So with this, your Jupyter Notebook testing is done. I think it was a very easy Jupyter Notebook testing. Okay, as compared to your MLOps project 2, that was your anime recommender system. Okay, so because our main focus of this project is not to learn a complicated project. Okay, our main focus is to learn advanced complicated technologies that I will be telling in the upcoming videos, where we will be creating our VM instance, configuring them, everything. Okay, it will be very complicated, I'm telling you. Okay, now let's jump to our next video, that is our data processing, where we will be using the same things that we did in our Jupyter Notebook testing, but just changing the approach. In the data processing video, we will be using classes, objects, a more modular way. Okay, so let's jump into it.